Everyone. So today we are going to go over chemical reactions. We're going to talk about writing chemical reactions and balancing chemical reactions. So here are a few different chemical reactions. Here we have your typical, like what everyone thinks that a chemistry lab looks like. Right here, this would be, we're burning something. Burning would be a chemical reaction. Here, this is called elephant's toothpaste. And if you're really interested, you can look up a bunch of really cool uh, demonstrations of elephant's toothpaste. It's like a foam substance that comes out of whatever bottle or container that you have it in. And then over here, it looks like we've got like the reaction of sodium and water. When I throw water into, or sodium into water, then you end up having a reaction because you end up producing sodium hydroxide. Okay. So we're going to talk about chemical reactions, but I want you to think about a couple of things. First, how do you know that a chemical reaction has taken place? Are there any specific indicators? For example, rust. Is rust a chemical reaction or is it a physical reaction? What about melting ice? Well, okay, rust, you are actually changing things. Okay. So, how do you know that a chemical reaction has taken place? There are some things that can happen in a chemical reaction. Maybe the way that something appears, the appearance changes. Maybe something changes in the taste or the smell might change. Could be a chemical reaction. Maybe heat is released, or maybe gas is released, or bubbles are released. So there could be a color change. There could be a release of energy or an absorption of energy. Or you could end up having a release of gases. Those are some specific indicators that a chemical reaction has taken place. Now, melting ice, we're not changing H2O into anything else. We're changing it into H2O solid, goes into H2O liquid because my chemical is not changing because of the bonds, them not changing, then therefore it is not a chemical change. It's a physical change. Okay, so what will happen to the mass after the reaction takes place? So when you have a reaction taking place, if you go all the way back to the very, very beginning of this course, we did a lab activity called Matter and Change, and we talked about the law of conservation of mass. The law of conservation of mass states that matter is neither created nor destroyed, but it can change where it is. So, for example, if I have H2O and I break H2O up into H2 gas and O2 gas, I am going to have the same amount of hydrogens on both sides, and I'm going to have the same amount of oxygens on both sides. So, in order to have that reaction, and we did this on your M&M lab, in order to have that reaction, I would need two H2O molecules to break down to form two H2 molecules and one O2 molecule or oxygen gas. Okay, so what happens to the mass after a reaction takes place? Mass is conserved. Mass does not change after a reaction takes place. So, what's the difference between a physical change and a chemical reaction? And this is something that we talked about in first quarter, but I wanted to make sure that we went over it again. A physical change is an alteration of the substance that does not affect the chemical composition. A chemical reaction is the changing of a substance where the other substances are different. I have broken bonds and I have made new bonds. So, physical change does not affect its chemical composition. Chemical reaction, the changing of a substance to other substances by breaking of bonds and the formation of new ones. Breaking of bonds and the formation of new ones. Now, your indicators for a chemical change are temperature change, color change, release of gas, change in odor. So, like food rotting, that's an actual chemical change going on in your refrigerator, or the formation of a precipitate. The formation of precipitate is when I have two liquids mixed together, they form kind of like a solid substance. That solid substance is called a precipitate. Okay, so again, temperature change, color change, release of gas, change in odor, or the formation of a precipitate. So when we're writing chemical reactions, we first need to start with what are the reactants and what are the products. The reactants are what we are reacting together, and the products are what is produced. So I have two different reactions here. The first one I have is glucose reacts with oxygen to produce carbon dioxide and water. My reactants are glucose and oxygen, and my products, what is produced is carbon dioxide and water. Now, on the left-hand side of the screen, you'll see I have NaCNS plus HClAq yields NaClAq plus HCN. Okay, so when I look at the basics of this reaction, everything on my left, my NaCN and my HCl, are reactants. Everything on the right are my products. Okay. When we read this reaction, okay, we read this reaction. The other thing I want to point out is I have this S and I have an AQ, AQ, and a G. S means solid, AQ means aqueous. Aqueous means that it has been dissolved in water, and G is gas. So S is solid, AQ is aqueous, which means that it's been dissolved in water, and G is gas. So I would read this reaction as solid sodium cyanide reacts with aqueous hydrochloric acid to produce aqueous sodium chloride and gaseous cyanic acid. Okay, so one is the word equation and one's the formula equation. The formula equation's on the top, the word equation's on the bottom. All reactions must follow the law of conservation of matter or mass, and that means that it needs to be balanced. So when you look at this boxed equation right here, when you look there, you can see I've pointed out the subscripts and the coefficients. You may not change the subscripts at all in a chemical reaction. The subscripts are what makes up the compound, and the compound is formed based on valence electrons and how a bond is formed. But the coefficients, that's what you change in order to balance a chemical reaction. Different symbols can mean different things. So we're going to talk about the different symbols. So here we have a chemical reaction. We have 2H2 plus O2 yields 2H2O. So what does everything mean? The plus means reacts with or adds to. The arrow means yields or produces. Think of it as if you're learning a new language, like you're learning Spanish or you're learning Mandarin or something. And so you're translating the English to the Spanish or the English to the Mandarin, or maybe even the Mandarin to the English. So in this case, we're converting the chemistry to the English. Okay, so when you have arrows like that, and the arrows actually, I'm going to put this up over here. The arrows for a reversible reaction actually look more like this, where you have half arrows. That's a reversible reaction, a reaction that can go either way. S is solid, L is liquid, G is gas, AQ is aqueous, which again means dissolved in water. And then heat added. Heat added, you would do an arrow with a triangle over it. That's heat added. And then finally, one last one is a catalyst being added. A catalyst is something that speeds up a chemical reaction. H2SO4 is a common catalyst, and you would write the arrow with the substance on top. So that's when a catalyst is added. Okay. And then at the very top with the triangle there, this means that heat is added. So when you're writing an equation, the word equation is the names of the reactants yields the products. So reactants yield products along with their states of matter. Okay, so I can go from the formula equation to the word equation and back again. So for example, in this reaction, I have H2G plus O2G yields H2OL. That can be written as hydrogen gas reacts with oxygen gas to produce liquid water. Hydrogen gas is your H2G, reacts with, that's your plus, Oxygen gas is O2G. To produce is your arrow. Liquid is your L. Water is H2O, or you could even say dihydrogen monoxide. Now, I've written here, don't forget your diatomic molecules, because when I say hydrogen reacts, I mean H2. When I say bromine reacts, I mean Br2. When I say oxygen reacts, I mean O2. Nitrogen reacts, N2. Chlorine reacts, Cl2. Iodine reacts, I2, and fluorine reacts, F2. So the skeletal equation is written simply just by writing the formulas and the symbols, and that's it. That's the skeletal formula. But notice that reaction is not balanced. I don't have the same number of oxygens on both sides. So when making a bike, you need a frame, wheels, handlebars, and pedals. Frame, wheel plus handlebars plus pedals gives you a frame, W2, which is wheels 2, because you need 2 wheels, handlebars 1, and P2, 2 pedals. So that's the skeletal equation. So when you're working in a factory and you're putting that bike together, you need 2 wheels for every 1 bike. You need 1 frame for every 1 bike. You need 1 handlebar for every 1 bike, and you need 2 pedals for every 1 bike. So that's going to be your balanced equation. Now, if we look at balancing things right here, okay, if I'm going to balance this reaction, I want to go back and forth and make sure that it ends up getting balanced. So that's what our balanced reaction is going to be. It's going to be 3NO2 plus H2O yields 2HNO3 NO. And the way I did that is I looked at my N on both sides. So one thing that I did in class is I have my reactants on one side and I have my products on the other side. So I have nitrogen, hydrogen, and oxygen. Nitrogen, hydrogen, and oxygen. And I figure out how many of each I have. So in the unbalanced equation, I have 1 nitrogen on one side, I have 2 on the other. I have 3 oxygens on one side, I have 4 oxygens on the other. I have 2 hydrogens on one side, and I have 1 hydrogen on the other. Okay, so the very first thing that I know is I know that this hydrogen right here, I have 2 and then I have 1. I can never make that 2 1. So I need to make that 1 2 by putting a 2 in front of my HNO3. By doing that, that also changes my nitrogen. Now I have 3 nitrogen, and I now have 6 oxygen, 3 times 2, plus 1, I have 7 oxygen. Okay? So then the next step that I need to look at is, okay, I look on the left side and I see I have 3 nitrogen, so I need to make this 3. So I make that 3 by putting a 3 in front of the NO2. Now that's changed my oxygens. I now have 3 times 2, which is 6, plus 1, I have 7. And now I look at everything and I go, okay, 3, 3, balanced. 2, 2, balanced. 7, 7, balanced. And that's how you balance the chemical equation, okay? So there are some basic rules for balancing reactions. The first thing that you need to do is determine the correct formula for all of the reactants and products based on what you know about elements and how they bond together. So this is why we started with naming and forming compounds, because you need to be able to write the compounds, either the name, or you need to be able to write the compound based on how elements will go together. Write the formulas for the reactants on the left and the products on the right, and then you're adding a plus sign for when they're adding to each other. Count the number of each element in the reactants and the products separately. Now, my one hint is to count your polyatomic ions as if they are one unit. That sometimes helps, especially if they stay together in your chemical reaction, because then you don't need to do all of that extra. It's a bunch of extra legwork if they don't split up, okay? And then balance the elements one at a time by changing the coefficients. Check your answers after that. Okay, so we're going to do some practice problems. Oh, and make sure, sorry, one last thing is you want to make sure that you have the lowest coefficients in the lowest whole number ratio for those. So here's an example. Aluminum reacts with oxygen in the air to form a thin protective coat of aluminum oxide. Balance this equation, the equation for the reaction. So aluminum reacts with oxygen, okay? Now remember, oxygen is O2, not just elemental oxygen, because that doesn't exist standard naturally in nature. Aluminum is Al. So aluminum reacts with oxygen in the air to form, so this right here, to form, to yield, a thin protective coat of aluminum oxide. So now we need to figure out what aluminum oxide is. So we need to think about what our rules are for bonding. Aluminum forms a +3 charge. Oxygen forms a -2. So the 2 swaps down and the 3 swaps down. I end up getting Al2O3. Okay. So when I balance that, I'm going to use the coefficients, use only coefficients to balance everything. Okay. So when I look at that, I want to look at that and I want to say, okay, I have 2 aluminums on one side. Okay. I have aluminum. I have 2. I have 3 oxygens. Aluminum here. I have 1 oxygen. I have 2. Now, for me, I personally like to balance my oxygens in this case first, and that's because I have an even number on one side and an odd number on the other side. So I need to multiply this. I need to multiply that oxygen right there by an even number to make that even, because I can never make an even number odd. So that's going to give me 6, and that's going to give me 4 aluminums. Now I'm going to balance the oxygens on this side. So I'm going to put 3 there. That's going to give me 6. And I'm going to put a 4 here for aluminum. And I'm going to double check. 4, 4, check. 6, 6, check. So my balanced chemical equation is 4Al solid plus 3O2 gas yields 2Al2O3. So here are some sample problems, okay? So we're not going to identify the reaction type. We're just going to balance the reaction. So here I'm going to look at my carbons on both sides. I'm going to look at my hydrogens, and I'm going to look at my oxygens. And I'm going to split it down the center, okay? So when I look at my carbons, I have 5 on the left side and I have 1 on the right side. My hydrogens, I have 12 and I have 2. And then for my oxygens, I have 2 on one side and I have 2, 3 on the other. Okay. So the next thing that I'm going to do when I have this type of reaction where I have CH something plus O2 yields CO2 plus H2O, this is a very common reaction type. It's actually called a combustion reaction. I like to balance my hydrogens first. That's what I like to start with in combustion reactions. So I'm going to multiply my hydrogen by 6 right here. Okay, so that's going to end up giving me 12 there, but then that's going to end up changing my oxygens. It's going to change my oxygens to 6 plus 2. It's going to give me 8 oxygens. Okay, the next thing I like to balance is I like to balance my carbons. So I'm going to balance my carbons here by putting a 5 there. That's going to give me 5, but then that changes my oxygens again. 10 plus 6, that's going to give me 16. Okay, so I have 16 oxygens on one side, 2 on the other. So now I need to balance that 2 out by putting an 8 here, and that's going to end up giving me 16. 5, 5, my carbons check. 12, 12, my hydrogens check. 16, 16, my oxygens check. Okay. Now, this next question is going to be a little bit easier to balance because it's a double displacement reaction, and I find double displacement reactions easier to balance. So I'm going to look at, I have my K, my Br, I have my Sr, and I have my O, okay? And I'm going to look on both sides. So my K, I have 1 and then 2. My Br, I have 1 and then 2. My Sr, I have 1 and 1. and my oxygen, I have 1 and 1. So my thing that are not balanced are my KBr. So I can put a 2 there, and that gives me 2 and 2. Now I have 2, 2, 1, 1, check. So in this case, I just have my coefficients are 2, 1, 1, 1, okay? But I don't write ones because that's kind of redundant. So let's look at some more sample problems. Write the balanced formula equation for calcium and fluorine yield calcium fluoride. So calcium is just that, and actually calcium regularly exists as a solid at room temperature, and fluorine. Now the thing to remember with fluorine is one of your diatomic molecules. So F2, okay? That's your H. Broncliffe or Hofbrinkel or Brinkelhoff, all of those, whatever way you remember it, that's one of your diatomic molecules. Remember, they are H, Br, O, N, Cl, I, and F, okay, yield calcium fluoride. So calcium forms a +2, fluoride forms a -1. So I need 2 fluorides for every 1 calcium. And then I look at this and I have 1 calcium on one side, 1 on the other. 2 fluorines, 2 fluorines. It is balanced. Perfect. Okay. Now, chromium 3 phosphate and sodium yield. So I'm going to start with my easier one. Sodium is Na, chromium 3 phosphate. Well, chromium is a +3. That's what the 3 means right there. Phosphate is PO4 with a -3. So +3 -3, awesome. They cancel each other. So I get chromium phosphate, CrPO4, plus sodium, yield chromium and sodium phosphate. Sodium forms a +1. Again, phosphate forms a -3. So I have Na3PO4. Okay. And so then remember earlier I said keep my polyatomic ions together because I see I have 1 PO4 on one side, 1 PO4 on the other. So it's balanced. 1 Cr on one side, 1 Cr on the other. 1 Na and 3 NAs. So I'm going to put a 3 in front of my Na there. Okay. And that's going to balance that one. And then our very last practice problem. Lithium nitrate yields lithium, nitrogen, and oxygen. So here it's important to pay attention to which ones of these are diatomic. Nitrogen and oxygen are. So N2 and O2. Lithium is just Li. So lithium nitrate, well, Li forms a +1 charge as an ion. Nitrate forms a -1 charge. So +1, -1, they cancel. Lithium nitrate, LiNO3, yields lithium, Li plus N2 plus O2. Okay. Now, what I notice here is I notice I have an odd number here and an even number here. So that's my odd even problem again. So I'm going to have to make this odd number an even by putting a 2 there. That gives me 6 oxygens on this side. If I have 6 oxygens on this side, I need 6 oxygens on that side. Well, here I have 2 nitrogens. I have 2 nitrogens. 2 lithiums, so I need to put a 2 there. So my balanced equation is 2LiNO3 yields 2Li plus N2 plus 3O2.